So far we talked about the issue of localization, the problems and the history of navigation in the past, all the way to 4,000 years ago, and difficulties in knowing where you are in general, and try to formulate mathematical formulation for the position and orientation of the robot. In other words, the pose of the robot, going from k to k plus 1 to k plus 2 and so forth, and adding two elements of randomness in the measurements of the position and orientation of the robot. In this third lecture on localization, we will try to get as accurate as possible an estimate of the pose, the next pose of the robot using Kalman filtering. So let me go to the station here, and what we see here is that the problem we face, just like the ship's navigator, is how to best estimate our new pose given the previous pose and noisy odometry. Noisy measurements of positions, x, y, and orientation, or the orientation theta. The mathematical tool that we will use is Kalman filter, which is described more completely in Appendix H, which I briefly showed it to you in the first lecture. This filter provides the optimal estimate of the system state, position in this case, x and y, assuming that the noise is zero mean and Gaussian. In this application, the state of the Kalman filter is the estimated configuration of the robot. And it is going to be a recursive algorithm, which means every step go from k to k plus 1, one filter is designed for it. And then k plus 1 to k plus 2, another filter is designed. So you have as many steps as you take to reach the goal, that many filters have to be designed in real time on board of the robot. And the Kalman filter then is formulated for linear system, but our model of the robot is nonlinear, as we said before. And what we do a linearized model. We use a Taylor series expansion here, and we linearize the equation 6.3, which you saw before, involving cosine and sines and many other nonlinearities, so that the estimate of the location, approximate estimate of the pose of the robot at k plus 1 is the old position plus a Jacobian matrix. F of x is the Jacobian matrix. Partial fraction of f, which is the pose function, with respect to x and y, times the difference between the x and the estimated x. Okay, and plus the Jacobian of the pose function with respect to the variance, the uncertain vector v, times the v itself. Remember, we originally assumed v equal to 0 at the very beginning. With respect to the current state x hat, which is here, fx and fr are Jacobian matrices, which are vector versions of derivatives, as we said before, which are sometimes written as partial of f with respect to x, partial of f with respect to v, or a gradient, that upside down triangle you saw, gradient of f with respect to x and gradient of f with respect to v. This approach is this approach is to estimate of a nonlinear system is known as extended Kalman filter, or EKF. Jacobians are also reviewed in Appendix G, which you saw before. So I strongly recommend to you, don't wait for the homework to arrive. Read those appendices, and then read chapters. Okay. The Jacobian is calculated based on equation 6.2 with respect to x as this value, when v is equal to 0. Okay. And then, of course, this is the history of basically Professor Rudy Kalman, which was born in Budapest, Hungary in 1930, and spent his education at MIT for a bachelor's degree and master's degree, and PhD from Columbia, 1957. And as I mentioned to you, in 1960, he published a paper here called A New Approach to Linear Filtering and Prediction Problems. Okay. This was published in 1960 time frame, not in IEEE, because IEEE was not very kind to him for his sometimes provocative approach to his discipline and in the conferences. I may have told you about some issues he had with fuzzy logic, for example. But he had accepted my invitation to be at my conference in 2018 in Prague, Czech Republic. So this was not published in IEEE by his choice and published in ASM. And he has received IEEE Medal of Honor, Toyota Prize, which is equivalent to so-called Japanese Nobel laureate, Nobel Prize, and many other accolades. The second Jacobian is partial with respect to V, the uncertainty vector V, which is given by equation 6.5. Then the vehicle object provides methods to compute f of x and f of v like this. Vehicle dot f of x for this initial pose and the next pose, the incremented values of v, and you have obtained this matrix, which is equivalent to this matrix right here. Okay. Well, the first argument is the state about which the Jacobian is computed, that's the nominal values. And the second is the odometry measurement for d and for theta. Okay. So you're talking about 0.5 centimeter and 0.1 degree. Okay. We now can rewrite, extend the Kalman filter prediction equations. Again, refer to Appendix H. The next pose of the robot is obtained by x of k, x hat of k plus 1, given values at k, which is obtained by this function. And the covariance matrix is also updated. The next value of the covariant matrix is obtained by equation 6.7. And it describes how the state and covariance evolve with time. Okay, so the important thing about Kalman filtering here is that as you move from one time incident to the next step, not only your state changes, but your randomness also changes. So your covariance matrix changes too. And that is one of the unique features of Kalman filtering. The term x hat k plus 1 given x is read as the estimate of x hat, y hat, and theta hat at time k plus 1 based on the information up to and including time k. So all the previous history up to k is used to estimate k plus 1. Okay? Which is really, really remarkable issue. P hat is the covariance matrix representing uncertainty in the estimated vehicle configuration. And the second term in the equation 6.7 is positive definite, which means that P hat, the position uncertainty, can never decrease. In other words, it's just the beginning of your headache. The uncertainty keeps changing, and it may very well increase rather than decrease. Okay. So that's the interpretation of the second term. Now, V hat, which is this value, is our estimate of the covariance of the odometry noise, which in reality we do not know. So we don't know V hat either. To simulate the vehicle and the extended Kalman filter using the toolbox, we define initial covariance matrix to be quite small, like this, since we assume we have a good idea of where we are to begin with. Okay, so that probably makes a good sense. Because let's say you have a robot in a war zone and you want to send that into enemy territory. You know where you're going to release the robot and let it go. So that's it. So that's the initial goal. Okay. So then you use extended Kalman filtering using the vehicle dynamic and the assumed V and the assumed initial pose. And then you run it for 1,000, let's say, running the filter for 1,000 time step, you run it like this, for 1,000 time step, going from initial condition or initial position, origin to the destination. And the way you do that, you go and plot it, equation 6.4, you hold the plot, and you keep running it for basically, in this particular simulation that I'm about to show you the result, you have 1,000 Kalman filters are designed, each step. Okay? Which is really very powerful thing. And you can look at the history of that covariance matrix and other parameters x, y, and theta at any time step between 0 and 1,000. In this case, 700 time step. So let's look at the graph. This graph let's see, I can even make it a bit larger. Okay. So let's look at this graph. What is going on here? The destination is 0, 0. You want to go to this point. And you want to have the pose to be 180 degrees, looking left. Okay. And you're currently located right here. This shows a finite number of steps of the estimation of the location of the robot. Basically, equal those number of ellipses you see. This is one center of this ellipse right here, the first ellipse. That center right here is the first one shown in this figure. The maximum error in estimating that new pose is from here to here, and the minimum is from here to here. Basically, the larger and the smaller axis of the ellipse. Now, I think I have to backtrack. This actually is not for this one, it's actually for this part. Okay, the first one you see is this one, right? The big one. Lots of error. Okay, a big time error. And then the next one, you go around and become this one. Okay, this one. And then you come here and become this one. Watch me tracing this sequence of ellipses. Then you move around the trajectory, you come to this center. That's your first, second, third, and fourth pose. This is your first, fourth pose, and this is the uncertainty. And then here you go to this. And then you go to here, you get this one. You come to here, and you get this one. You come down, and you have this one. And you come to here, and you get this smaller one. Then you come here, and you get here. Just always look for the center of the next ellipse. And then you come here and you go to the center of this one, you get this one, you go move around, and then you go to here, which is the center of this ellipse, and you go to this one, you go to the one that I mistakenly gave you indication, and then another one here, which is this one, another one here, which is this one, and then you have this one. As you can see, the error keeps going down and finally becomes very, very small, like a line, and then you are home. Okay? Where you see that magic fingers is the final location. That's the end of 1,000 estimation. Okay? Recursively going and keep redesigning a Kalman filter as you go on. In many physical problems, you launch let's say, a satellite into orbit. Okay, you put it on a rocket and you launch the rocket, and each so many time steps. I don't know. It could be a few seconds, or maybe a few minutes, or maybe 1 hour. I don't know for sure. You keep recursively estimating where you are located, where the rocket is located in the three-dimensional space. Okay. And then what you want to do is when you reach the orbit to release your satellite, you want to minimize that deviation. Hopefully somewhere like this. Okay, that's the idea. Okay, now let me reduce this now back to this chart is the overall uncertainty which is given by a square root of determinant of the covariance matrix, which shows monotonically increasing uncertainty, which is blue one. Okay, that is for sigma equal to 1, or alpha equal to 1 rather. Then you have two other curves, alpha equal to 1/2, which is the red one. If you have low deviations, you will expect to have better results. Okay, and uncertainty is smaller. And if you have a very large one, like 2, twice the nominal value, you get this green curve, which is even worse than the blue, which corresponds to sigma equal to 2. Okay. Now, so far we have not used a map. We have assumed that the robot doesn't know its world space. Okay, robot doesn't know the environment. Okay, many applications are like that. As I mentioned to you, you are in a battlefield and you want to send the robot to your enemy location. You don't know where you are. Okay, and also these days you may have some idea where you are because you have the satellite moving in the space, but sometimes you actually don't know where you are. In indoor robots, like in the lab for your experiment number 3, the robot knows exactly how many tiles are around it. Okay, let's say in this case you have 10 by 10 set of tiles, and if next time you go to the A side, you see a whole portion of the floor has been set aside. That's because that's the workspace of the robot. Okay, and you will design hopefully not 1 but 2 controllers in experiment number 3 based on your homework number 4. It will come in handy in experiment number 3. Okay. So we have seen how uncertainty in position grows without bound using dead reckoning alone. The solution, as the Phoenicians worked out 4,000 years ago, is to bring the new information from observation of known features in the world. In other words, start from a very modest, unsophisticated map. As you move from and estimate new locations, you bring those ideas, put it on the map, and you keep creating a map. Okay. In the examples that follow, we will use a map that contains n fixed but randomly located landmarks whose position is known. It's exactly like I described to you in last lecture in visual SLAM, where you already have gone to a location, you have got a whole bunch of landmarks which are reflected in your image database of that environment, and then next time you come, it will help you a lot. Okay. The toolbox supports command map. So let's say you have map 20,10. In this case, contain 20 features uniformly randomly spread over a region which is plus or minus 10 meters, which is this one, in the x and y direction, and this can be displayed by map.plot. You can plot your map. The robot is equipped with a sensor that provides observation of the features with respect to the robot as described by this function. So the equation which is relevant to your measurement by the sensor under the presence of sensor noise, in this case W, in equation 8, is described by this nonlinear function, which are a function of xv, the vehicle state, xf, the known location of the observed feature in the world frame. For example, xf could be the location of light tower along the coast of the water. And omega is, as I said before, is the noise. To make this tangible, we will consider a common type of sensor that makes the range and bearing angle to a landmark in the environment. For instance, a radar or a scanning laser rangefinder, such as this equation right here. Now, we need to, in the experiment number 3, we need to, and the homework which I'll give you on this subject, we will try to give you the parameters of either Pioneer or the Turtle robot in the lab, so that you will be simulating something which later on, hopefully, you will going to experiment on. Okay, so we may not have this scanning laser ranger on the robot. We do have many sensors on the Pioneer robot, and we have similarly on the other robot, and both of them have access to Kinect cameras for images. So for The sensor is mounted on board the robot. Observation of the height one is given by this. This is the equation for that particular sensor, which is this one. So I will check with my assistants, Ikram and Berat and possibly Dr. B. Benavides, to extract that information from the manual of those robots and give that to you. Okay. So that this may be only true for that sensor. We'll have expression for new sensors, which we actually do have. So Z is the vector of R comma beta, where R is the range and beta is the bearing angle, and the measurement noise is given by this covariance matrix. The standard deviation of the R and range and the standard deviation of the bearing angle. And for this example, again, we use sigma R 0.1, sigma beta is 1 degree. Remember, R is for the distance and beta is for the orientation. Therefore, you have degree. Giving a sensor covariance matrix given by this. And you can also have a command for this particular sensor called range bearing sensor, like this. Okay. You know, in ideal case, you know, we've tried in previous time that I've been teaching this course. Perhaps I will include that in future. You as hopefully future robot engineers, which is what you are learning here, you can actually look at the actual sensors in the lab and create an equivalent command for it and add it to the robotic tool. You could do that. Okay? And this is, of course, too late for this semester. I would have counted this as project number 1, for example, for some of you. But that means that you need to be ahead of the class in advance of the lecture, and that also is another issue. Anyhow, you can read that sensor by calling it sensor.reading, and you call I, and I is the time step. I is an integer. Since the map was created with 20 features, it shows that the location of the 18th feature. So you go to the extended Kalman filter, you write this equation, and you find you expand in a Taylor series expansion of this equation right here, with respect to xv and xf and w, and you get this equation like this. Okay. And equation 6.1 is now a linear equation, because h of x is known. H of x is always evaluated at the current estimated location. You know where you are. So it's just a number. This matrix and this matrix are known values. X and x minus hat is a linear function. These are the Jacobian matrices, Hx and Hw, expressed here. And then you go to the range sensor. Object above includes methods to H to implement it, implement equation 6.9, which is this equation. Equation, let's say 6.9, this equation, implement that. And then these are the rest of the Kalman filtering equations, 2 here and 2 here, where K is the Kalman gain, and P is the covariance matrix, and S is the innovation matrix. and you go through the sequence of commands. This is what you get right here. This diagram shows 20 obstacles, as you see in these small, segments, small, those, I don't know how to describe it, but it's like a twisted square. You go from here to here, to here, to here, to here, to here, so forth. So this is a bit similar to the homework I gave you today, except instead of 20, you only have 2 obstacles in that homework. And you need to move from point A to point B in that figure I gave you in the homework, avoiding those 2 obstacles. Okay, so this is the result of using a map of 10 by 10 area right here and 20 obstacles. Okay, so this is the third lecture, end of the third lecture on localization. We won't have a homework for a while on it because we're busy with other things. Experiment number 2. I assume homework number 3 is finished. It's been uploaded. Homework number 4 is you start with it today. And experiment number 2, you're already signed up. And you can do the work with the ABB robots, manipulators. And Ikram has been almost successfully finished a snake robot in the lab, as you saw a bit of video on it last time. He also has attached a snake robot to the end effector of the ABB robot. So moves as manipulated robot moves and the snake moves and he goes around into 3-dimensional space. So if some of you would like to do that, you have to convince Ikram to work with you and show you how that works, okay? And in your experiment, I want you to videotape your experiment. From anything you do, videotape it. Experiment 2, experiment 3. Later on, we can put it on the YouTube and people giving credit to the team and everybody can watch. Okay, we'll see you next week.